It's a bird. It's a plane. It's a super Earth? Perhaps one of the most revolutionary discoveries in modern astronomy is the discovery of an entirely unpredicted class of planets known as super-Earths. These rocky planets mass from anywhere between 2 to 10 times Earth's own mass and are believed to have a rocky core, and some might even be better suited for life than our own planet. It was initially believed that the most common type of planet in the solar system were gas giants. It was a gas giant, after all, that was the first exoplanet ever discovered by mankind. However, as our ability to spot planets in other solar systems has increased, scientists made a shocking discovery. It wasn't gas giants or even small rocky planets like Mercury that were most common, but rather large rocky planets. Though as smaller planets are more difficult to discover, our findings may still be accidentally biased. So why did scientists go with the term super-Earth? The name comes from the fact that along with the rocky core, these planets are able to retain a significant atmosphere, features only found in 2 planets in our own solar system, Earth and Venus. However, the name can be misleading, and many have fundamentally misunderstood the nature of a super-Earth. When you think of a super-Earth, after all, you're probably thinking of a planet that's largely like our own Earth, rocky with oceans and a welcoming atmosphere. But that's not what super-Earths are at all, or at least that's not what most super-Earths are like. 55 Cancri e, for example, is a super-Earth completely covered by an ocean of lava hot enough to melt iron, basically making it the Mount Doom of planets. Meanwhile, Gliese 1214b is believed to be the polar opposite, a water world completely covered by an ocean. Within these 2 extremes, scientists have found a plethora of worlds. Initially, scientists believed that super-Earths could be super-habitable and even have better conditions for life than our own planet. Their increased size would offer more surface area for life and be less perturbed by the gravity of nearby objects, and thus offer more climate stability to its inhabitants. On our own planet, the leading cause of extinction is climate change, with periodic ice ages wiping out vast numbers of species. At the time, it seemed like the name super-Earth was quite apt, as these worlds would be far more habitable than Earth. However, as scientists refined their knowledge of the physics and geological processes on these super-Earths through experimentation, a different story began to emerge. Firstly, the sheer mass of these planets means that many of them are bound to be water worlds. The increased gravity would attract greater amounts of icy comets than our own smaller Earth did, leading to planet-spawning oceans that could be miles deep. And what's wrong with that, you might ask? After all, life almost certainly began in the ocean on our own planet, and the ocean remains far more biodiverse than land does. More water should mean more life, right? Well, the biggest problem with a large water world is that the increased gravity and great depth of its oceans would smash water molecules together into ice formed not by low temperatures but by incredible pressure. This extremely dense layer of ice would act as a form of sealant around the rocky core of the planet, blocking off the core from the surface and shutting off the carbon cycle for the world. This may be biased toward carbon-based life forms, but even if non-carbon-based life forms are possible, this thick layer of ice would shut off vital minerals regularly exposed by geological processes on smaller worlds and prevent them from entering the biological life cycle. Even if you aren't covered in water, that big gravity field is gonna be a problem for the exact same reason. A super-Earth is going to attract a lot more celestial objects and thus be prone to much more extinction-level events from asteroid impacts. While that wouldn't preclude life entirely, cyclical extinction-level impacts certainly would make the evolution of intelligent life extremely difficult, if not impossible. Super-Earths could also be prone to attracting more gas, and thus have much thicker atmospheres than here on our regular old dumb Earth. A much more dense atmosphere comes with a whole host of problems, and we need to only look at Venus for one very good reason why a super-Earth with a thick atmosphere would be uninhabitable. Temperatures on the surface there are hot enough to melt lead, and while the planet is closer to the Sun than we are, it is still well within the habitable range of our Sun. Venus's thick, oppressive atmosphere is the real reason for its uninhabitable surface temperatures, and a super-Earth with a similarly thick atmosphere would likely suffer from the same life-killing global warming effect. Another nail in the coffin for super-Earth habitability is the effect of the planet's mass on its core. Our own core is only partially molten, and its rotation maintains a powerful electromagnetic field which protects life on Earth from cosmic radiation. On a super-Earth, though, the massive pressures at the core from the increased mass of the planet makes it extremely unlikely that its core would remain liquid for very long, perhaps only a couple of billion years, before it inevitably solidifies into a solid core. While life certainly could evolve during the time the core was liquid, it would find it very difficult to survive as the planet's magnetic field weakened and eventually collapsed entirely. DNA is very delicate, and while some radiation is good to promote mutations that can spur on evolution, too much radiation leads to the breakdown of DNA. Life on a super-Earth with a solid core would likely only be very simple and only exist in places shielded by cosmic radiation. However, it's not all doom and gloom, and super-Earths could possibly give rise to a void ecology, or life that exists in outer space. So we know there are organisms from our own planet that can exist for a short time in space, so the idea of a void ecology is not completely out of the question. However, the problem with looking for spacefaring life forms is that, as far as we know it, life cannot get started in the extremely harsh environment of space. It must start somewhere more hospitable, and then make the move to space. Super-Earths with solidifying cores could be the perfect nursery for a void ecology, with organisms becoming increasingly resistant to cosmic radiation via the slow, multi-million-year process of its planet losing its magnetic field. All it would take then is a lucky asteroid impact to knock debris infected with these life forms into outer space, an improbable but not impossible proposition. However, for life as we know it, super-Earths are looking increasingly unlikely to be hospitable. But scientists have high hopes for a class of super-Earths that range in the low end of the scale, with a mass only as twice as big as our own Earth. These smaller super-Earths have many of the advantages of larger super-Earths: climate stability, longer molten core lifespan, larger surface areas, without the disadvantages of being as big as their larger cousins. These super-habitable worlds may end up being havens for life, even intelligent life, though the increased gravity would make rocketry more difficult and expensive, perhaps greatly delaying or even preventing a species from ever making it to space. Earth may turn out to be a backwater planet that's barely habitable by alien standards, but seeing as it's the best we got in our galactic neighborhood, we'd better start taking problems like global warming and pollution seriously, because there's nowhere to run to. Now go watch Space Chief makes shocking alien confession, or click this other video instead.